This space here, this here.
Guys, you don't actually need to use the temperatures. I've already given you the data from the station. One more minute and I'll give you an answer. Do you guys want to answer, or do you want to wait a few more minutes? Do you want to finish trying? Hands up people who want to answer now. And hands up people who want to continue trying for a bit more. Okay. Give you 30 seconds more then. Half. Alright, so remember the assumption is quasi-static expansion, so it follows ideality. If your work done, volume work done equals the integral of PdV, and you have your constant P0, take your P0 out, so you integrate for the volume change. It's P0 times V2 minus V1. So you've done this already. Since total volume is mass times the specific volume, so you have 10 pound mass of that gas. You multiply it by the specific volume of 1 pound mass. So you can put that in your equation. Your volume work equals your mass times your pressure times the volumes, the two volumes, V2 minus V1. So your volume work equals 10 pound mass times the pressure, which is 60 psi. Psi means pressure at and basically the actual pressure, not the gauge pressure, times 8.354 minus 7.486 times 1 over 5.404 to convert to BTUs. Yeah. So 1 BTU to 5.404 psi per cubic feet. Yeah. That's one of the difficult parts. And then you can convert it to kilojoules by multiplying by 1058. I think. But anyway, you can look that up. I was going to get you guys to look that up anyway. Anyone confused? Okay, go for it.
Why are we using the pressure of the gas inside and the gas outside? When the gas is actually expanding against the atmosphere.
Yeah, but your pressure is it's the pressure inside the cylinder. So if I go back to the question, so your steam is at 60 psi, right? And you decrease the temperature, but not the pressure.
Yes. Okay.
So volume changes. Yeah.
Yes.
It's isobaric. Any other questions? You can ask after if you wish, but I mean, if you're confused, someone else is probably confused too. All right, shall we move on? Get a bit more lecture in, and then we'll finish the lecture and do 1 or 2 more questions tomorrow. Yeah? So, isothermal processes. This is where your temperature remains constant, right? So, same, we're just going to go through the equations, I think just to provide to teach you the concept. It's the exact same process, it's the same equation, PdV, and you drive for constant temperature. So, you know what isothermal process is? It's when your temperature remains constant, so your P is directly proportional to P in relation to V, T, and the number of moles. But because your T remains constant, then it's just proportional to volume. And your number of moles is always constant when you know it's either 1, 2, 3, 4, 5 moles. You can calculate P from the equation of state. In this case, it's the ideal gas law in this course so far. So going through I'm going to go through the divisions. Your volume work equals minus PdV, integral of PdV, right? If you have the ideal gas law, simplest equation state, P equals nRTV. So what can you do? It's an isothermal process, temperature is constant. So your P equals nRTV, and because your temperature is constant, you don't need to consider its integral, because integral is your change. So minus nRT integral of dV over volume. So you can integrate the previous equation. I think you guys have integration tables, right? Can I get hands if you guys have integration tables and know how to use them for this kind of integrals? Hands? No integration tables? Okay. But you guys know how to do these kind of integrals? Hands? Okay. I might try to get you guys integration tables. I used to have them from back in the day. So remember Boyle's law. Actually, do you know when Boyle came up with his law? Random fun fact? No? Anyone? Yes? Slightly before that. 1664. So, very. Imagine doing this back in the day. Anyway, sorry. Thought fun fact for you guys. Maybe not that fun. So Boyle's law: P1 V1 equals P2 V2 equals PV, right? So your pressure and volume are directly proportional when temperature is constant, and then inversely proportional to temperature. So P1 V1 over T equals P2 V2 over T2. For the above equation, you can basically convert the above equation for change in pressure. So volume work equals nRT log of P2 over P1. So as long as you know the ratio of P2 to P1 or V2 to V1, you can calculate the volume work. That's strange. So property ratio that I just mentioned, you can basically modify that. You need to comply with the first law of thermodynamics. The internal energy equals Q plus volume work. Now, this one's important. In an ideal gas, the internal energy is related to temperature, right? So, since the temperature doesn't change, so remember, it's the change in temperature. Since the delta U equals, hence the delta U, the change in internal energy equals 0 because the temperature is constant. So your volume work equals the heat dissipator entered into the system. Now, if you can calculate this as the area under the graph, so it's effectively your integral is basically the same, just more accurate version. So you can use the trapezoid method if you know it. I think I can provide a method of doing it, but personally I don't like it anyway because it's not very accurate. But if you do it in the exam, you'll get the marks for it. So area under the graph. Now, do you want one more example, or do you want to go home? Example, hands up. Home, hands up. Is it cool? More people. It's the first lecture. You guys can go home, but I'll give you that example tomorrow, and then I'll give you some more lecture slides, and then we'll do more examples as well. Yeah.